solutions.
So basically, the professor and I like don't want the solution to like floating around because generally like he teaches a lot of sections and basically each section each year like he has very similar midterms and finals. So I'm not able to like send you a solution or I mean I do can like settle a time or like we can discuss like a appropriate time and we can probably meet in person or something and we can go over your personal exam paper and the solution.
That works.
Okay, sure. Just send me an email about like when you're available to do that, right? But in another sense, like the final exam is not cumulative, so it it does useful to like go over the solution for the midterm. But now I guess you should put on your focus more on the class materials being discussed during the second half of the semester. Like it's cumulative in a sense. You have to know like what is a t-test, what is a p-value, how to check independence, how to get the critical value from the table, those sort of thing, right? It's kind of cumulative, but it's non-cumulative in terms you don't have to do some probability calculation. You don't have to understand like you don't have to memorize the formula of the probability density function of a binomial distribution, right? So the focus will shift more to like regression analysis, and that should be the priority for the second half of the semester. But again, I mean, it's useful to go over the solution, so I will do it. 你可以过来，就看不到的，都看不到，挡完了的，没关系。Any other questions? By the way, for the midterm, we have the mean of around 49%, the medium 46.5%. So I mean those are some statistics you may be interested in, and you can compare your own grade with the mean and the average to see if you're on the right track of the course.
So the total marks should be out of 100, right?
Yeah, it's percentage point. Like the numerical grade is out of 120. So basically we have 7 questions. We have 6 questions, each worth 20 points. So that's 120. And then we have one bonus question worth 20 points. But the bonus question like is not calculated if your total grade is above 120. So basically you have a score cap which is set to 120. However, if you get something, I mean I get 80 out of 120, but then I get a 10 out of 20 for the bonus question, then my total grade would be 80 plus 10, which is 90 out of 120. So basically the total mark for the exam is 120. And I have your numerical grade. Use your numerical grade divided by 120 to get your percentage grade. That's how it works.
But I thought that the bonus question like won't count even if you get that wrong. So ultimately the total test should be out of 100 only.
Yeah, we have, but again, we have 6 questions, 6 non-bonus questions. So that already set the total points to 120. It won't be 140, but it is 120. We have 6 questions, non-bonus. Yep.
Also, the mean was 50, right?
Sorry, the mean?
The mean was 50, right? 49.
49%.
So, like, that is that B or like is that C according to this John curve?
I'm not pretty sure about the curve, but I would say like around 30%, 30 to 35% of the students would get a and an A minus grade. So if you look at the medium, which is around 47%, and that would be, I guess, would be in the B range, of course, in the B range, and most likely a straight B grade, I think, if you get a 47%.
Okay.
Yeah, that's all the like reasonable guess I can make here. I'm not sure because I don't like I don't curve up or down for the exam, and like the professor, that's his job, and um, it's gonna be curved like like your grade would be based on like the relative performance. Um, so, for example, the exam was very difficult. So even though you don't get a perfect numerical grade or like a percentage grade, however, you performed like much better than the average of other students, then you get a high grade. So it's based on the relative performance. That's the point.
Okay, okay. Thank you so much.
Any other questions about like this week's homework or like midterms, anything?
Can we go through the like general method of solving the like last assignment 7?
Sorry, assignment 7, which question?
Like both of them, but like the general way that yeah, this is right, this is right. So
Like I think like the first question is quite straightforward. The t-test, like you already did some t-test assignment before, but like it's a one sample t-test, and in midterm exam you did another one sample t-test question. Like here you have a two sample t-test, um, and the characteristics of like a two sample t-test is you have two set of data, and each of them could have different sample size. And in this case, for the first set of data, you have like 12 sample size, and for the second one, you only have 11 sample size. That wouldn't be a problem for doing a t-test because two sample t-test, you can have two data set with different sample size. And with those data, you can calculate the sample mean, the sample standard deviation, right? Everything you need. Um, Something should be kept in mind is when you calculate the sample standard deviation, you utilize the formula of how to calculate the standard deviation. In the denominator, you have to use n minus 1, right? Because it's a sample and it has 1 degrees of freedom. So in the denominator, it's n minus 1 instead of n. If it's a population standard deviation, then the denominator would be n. And then you can check the formula on your slides on how to do a two-sample t-test. Basically, you have everything you need. You have two sample standard deviation, have two sample means, you have two sample size, and you can calculate your test statistics, which is a t-statistics, and you compare that to the t-table, which you already did from last homework assignment. And for part B, it's a rank test. So rank test, it's kind of useful when your sample data is not strictly normal. So when you have a scaled sample data, it's even more preferable to do a Wilcoxon rank test than a t-test. So what we have is we want to find the expected rank of two different groups. Like for first group, I have 12 numbers. For second group, I have 11 numbers, which means if we rank them, I have a total of 23 ranks, right? From number 1, 2, 3, 4, all the way to 23. However, I want to find the expected rank of a specific group, considering they have different sample size. So that's the most tricky part of the question. First, our null hypothesis is those two groups are pretty much the same. They don't have any difference. And we put that in the context of the rank. That means basically the first group and the second group should have similar ranks. That's the intuition of the question. And for example, I have 50 students in a class. 20 of them are boys, 30 of them are girls. And my null hypothesis is like the boys and girls perform similarly during the exam. Like those two groups have no difference. Then what I'm gonna do is I'm gonna rank the grade of those 50 students from 1 to 50. And then I find the expected rank of those 20 boys and the expected ranks of those 30 girls. Similarly, like for this question. And basically you can refer to your slides on how to calculate the expected rank of a specific group. By the way, it's a function of the total ranks and the sample size of that group. Then on our slides, we also have how to find the variance of the rank. And then you're gonna do a z-score test, right? Remember, you have an expected value, you have a variance. Then you can take the square root of that variance, you get a standard deviation, and you find the exact rank of a group. So basically, you have your x, which is your exact rank of a group, and then you have your mu, which is your expected rank of a group, and then you have the standard deviation of the rank. So basically you have all three parameters needed to do a z-score test, x minus mu divided by sigma. You have everything you needed to take a z-score test, and then you get your calculated z value and compare that to the z table. And again, if your p-value is more than 5%, the standardized p-value, then you reject the null hypothesis that the two groups are actually the same. A good intuition, for example, if I have 23 numbers of observation in total, the first group 12 number of observations. If they ranked from 1 to 12, meaning they have the 12 highest productivities. And then for another 11 number of observations, they ranked from 13 to 23, which means those groups, the second groups, their ranks are the 11 lowest productivity. Then I have enough evidence to reject the null hypothesis, because basically the first groups, all of them are good. Like they ranked from 1 to 12. In the second group, like all of them are bad. They ranked from 12, like 13 to 20 to 23. So, but that's just an intuition. Like in fact, you can't find that kind of perfect data set when one group is like stochastically systematically better than another group. In fact, in real data set, the ranks are kind of intertwined, but you can calculate the sum of those rank, the expected value of those rank, and basically that's Wilcoxon rank test. Again, you're gonna refer the formula for the expected ranks and the variance of the ranks. I think it's on your slide. And question 2 is very important. It's a chi-square test, and the chi-square test is a test for independence. If two things are related to each other or not. And in this case, what we have is like a specific illness and the ages. We want to find if there is any kind of relationships. Is there any dependence between those two variables? So again, our null hypothesis is I find nothing of those two groups. There's no interrelation. There's no like interactions between the two like the illness and the age. Like they are totally independent. That's my null hypothesis. And under that null hypothesis, what we can do is remember if we have independence, then the probability of A and B, or we can say the probability of A intersect B, is just the probability of A times the probability of B. That's under the assumption of independence. Here, exactly, we have that assumption of independence because that's our null hypothesis, so we can utilize that formula. So I'll do one example. I want to find what is the expected value of both illness, which means in that table, I would say yes, illness, and under 29 years old. So basically that's the upper left column of the whole chi-square table. What's the expected probability of that? First, we have our observation. Our observation says it's 48. Like in reality, there's 48 people who is 29 years old or less, however, who get this kind of specific illness. 48 is our expectation. 48 is our observation. But what's our expectation? We're gonna use the formula of PA and B equals PA times PB. We want to find the PA first. And let's assume A stands for illness, right? So what's the probability of PA? What's the probability of illness? I'm gonna use the total number of illness divided by the total number of people, which is 2,221 divided by 18282. That's the probability of having the illness. Then let's assume the event B is some person who is less than 29 years old. So what's the probability of B? What's the probability that a randomly selected person is less than 29 years old? Again, I use all the number of people who's less than 29 years old, which is 3,743, divided the total number of people. It's 18282. So now I have PA and PB. Under independence, what's the probability of A and B? What's the probability of a person both under 29 years old and having the illness? I just used PA times PB. I use those two probability and times them together. I get the probability, which is the expected probability of both illness and under 29 years old under our null hypothesis of independence. And we want to calculate the frequency using that probability, which is you do the calculation of PA times PB, and then you times the total number of people, 18282, and you get your frequency. So like the whole process is 2,221 divided by 18282 times 3,743 divided by 18282, and then times 18282. So you can actually cancel out like one denominator and one numerator. The 18202, you can cancel it out for one time, and your simplified expression would be 3743 times 2221 divided by 18282. That's your simplified version of how to find the expected value of that specific cell. Like that cell is the first row and first column, the intersection between first row and first column. And what you're gonna do is you have to calculate all the cells, all the expected number of the cells. I think you have like 6 cells, because you should be either yes illness or no illness, and then you have 3 kind of ages under 29, 30 to 49, and above 50. So you have 6 cells in total. You're gonna do that like what I did, but you do it 6 times, and you get your expected value. And under our null hypothesis, if our null hypothesis is correct, what we're gonna find intuitively is our expected value, expected frequency would be close to our observation. We did some kind of example before, like I think it's a bombing problem on Poisson distribution, right? We want to first we assume it's independence, we assume it's Poisson distribution, and we calculate our expected frequency and compare that with the real frequency we get from the data. Here we utilize the same kind of idea. We have our expected frequency, then we compare that with our observation. But here we have a more scientific way to determine if the two are really independent, because we have quantified what's the meaning of our expected frequency is close enough to our observation. We quantified what does that mean, close enough. We quantify that by using the chi-square statistics. And you can refer to your slides for the formula. It's chi-square, the chi like that Greeks, right? When you write it, it's a little bit like an X, an uppercase X, but it's pronounced by like chi squared. And you have a formula, pretty much is a difference between your expected number and your observation. You square that difference, and then you divide it by the expected frequency. and then you sum all the cells up. You sum all the 6 cells up. You get your final number would be your chi-square statistics, and you compare that to the chi-square table to find if the p-value is less than 5%. The degrees of freedom in chi-square table is columns number minus 1 times row numbers minus 1. And in this case is like the columns, we have 2 columns and 3 rows. So in this case, the degrees of freedom would be 2 minus 1 times 3 minus 1, which is 2. So you're going to locate, you have your chi-square data, and then you have your degrees of freedom. You can find everything you need in the chi-square table. And for part B, the relative risk of that illness is, that wording is a little bit confused, but I would say first you're going to calculate the absolute risk. For example, the group of aged 29 or less, right? You look at the first row, the absolute risk of getting that illness is just 48 divided by 3743. It's a probability, pretty straightforward. That's your absolute risk. And you can do the same for the like 30 to 49 age group and the above 50 aged group. You have 3 absolute risks, and you can take the ratio to find the relative risk. So basically, it's intuitively understandable that when your age is like older, when you're 50 years old or older, you have like a higher chance of getting that illness. So you're gonna find like the absolute risk of above 50 years old would be pretty high, and then you use that number divided by the absolute risk of like other groups, you would get a number greater than 1. So that's your relative risk. That means like my chance of getting that illness is higher than like 30 to 49 age groups and the less than 29 aged groups. So I have a higher relative risk. I think basically that's the homework. And I recommend you guys to try them like by yourself first before really like review what I said in the office hours, because in exam you don't have like my hints, and I have to do that independently and without any notes, right? You only have like a formula sheet. So, and those questions like the two sample t-test, the chi-square test, and it's all the fair game in the final exam, right? You're gonna may get a very similar questions in the final exam. So I think like from the midterm, I think they have a lot of questions similar to what in the homework, and um, that would go on to the final exam. So I think like the best way to prepare for the exam is to like absolutely understand all the homework questions without looking at my hints, right? So when you do your homework and after the exam, you review your homework. You don't look at your solution first, and if you want to find out if you can solve this by yourself independently, and if that's true, then I think you don't have to worry too much about the exam. But it's always a good practice to like spend some time with the homework by yourself first, and then you look at my hints and see if you get the correct method, idea, and solution. Yeah. Other questions about the midterms and the homework?
Thank you so much for your help.
All right. Uh, Good night, and stop recording.
Thank
Thank you,
you.
Victor. Thank you.